Hello and welcome to Making Sense of Charts with me, Mr. McIver, here at the London Central and North West Maths Hub. I'm talking about data handling in GCSE terms, the graphs and diagrams bit. And the important thing about any data set is you should always be asking, what's the story? And a good chart tells it really clearly. So here's a bunch of data. It tells us the annual RPI, that's Retail Price Index figures. If you're not sure what those are, I do have a video that explains it, so look it up. And this data tells us about average prices from 1900 to 1950. And just looking at that raw data, we can see that prices seem to be going up over time. Nothing very surprising there. If we look a little bit closer, we can see that there's a moment here when they go down and then they go up again. A chart can help to make this a great deal clearer. I'm now going to show all of this data on one simple line graph. Here is how the retail price index changed between 1900 and 1950. And when you look at it, you can immediately see that there are two very clear points there and there when prices began to go up. Look at the years when prices started to go up. 1914 and 1939, which you probably recognise as the start of World War I and the start of World War II. It seems that war is associated with higher prices. I cannot say at this point, my data proves that wars make prices go up. All the data shows you is there's some association between these two things. The general point I'm trying to make is that when prices are shown in the form of this line graph, it's much easier to see what's going on. Not only do we see that they shoot up at the start of each war, we also see that in between the wars there's a great big dip down here. It's not until 1940 that prices actually get up to the same level as they were at in 1922. You see why people talk about this period here as the Great Depression. Line graphs are especially good at describing what happens to data over time. We call this type of data time series data. If you have a set of time series data, try a line graph first. A good chart should also be clear. Here's a bar chart showing fiction book sales for a bookseller somewhere in North America. It's crystal clear what it's telling us. It's about fiction books, and it's broken into categories. We can tell this from those easy to understand headings. We can see exactly how much the different stock lines are worth. Back in 2006, romance sold 80,000 worth of stock. In 2007, it was up to over 110,000, and it seems to be settling round about the 80,000 mark. And we can tell all of that because the axes are so clearly labelled. If I'm the bookseller and I have a chart like this, it's pretty easy to see how I should organise the space on the shelves in my shop. Now this is a very simple chart. Don't underrate bar charts. They're the simplest, but they are often the best for showing data such as this, especially in this comparative bar chart or stacked bar chart model like we have here, where you have sets of different bars showing slightly different things. I'd now like to look at two slightly more complex charts that you might remember from GCSE, and the first one is a histogram. Here's a histogram showing you the mileage cover by a bunch of vehicles in a delivery fleet, and you can see from this chart very clearly that the data's very much bunched up between the kind of 15 to 25,000 miles a year. That could be quite useful to know if I'm planning how often I need to get my vehicle serviced as a haulage company owner. The other chart that's very useful is this one, a box plot. Here's a box plot showing the ozone levels in New York in parts per billion over the course of a single year. As you can see, it sticks out a bit to the right. We say that this distribution that stretches out to the right is in fact skewed to the right. If you look back at the histogram, it's kind of lopsided and stretches out to the left. That distribution is skewed to the left. How worried should we be about the ozone levels in New York? Well, let's have a look. According to the figures from the Department of Health, anything above 51 parts per billion is regarded as moderately polluted. So, for quite a bit of the year, well over 25% of the year, we're in the moderately polluted zone. And unhealthy for sensitive groups, when you look into it, actually means unhealthy for people like asthmatics, children and old people. Well, that's an awful lot of people. And above 101, that looks like a few too many days if I was a New Yorker. One thing we can take a bit of reassurance from is the fact that there only seem to be 2 data points right out on the end here, and just one of those, somewhere up here like 160 or 170, is clearly unhealthy for everyone. Before you move on, I want to make one very important general point about histograms and box plots, and that is they are really great at showing the shape of a distribution. One of these tails off to the left, so you can see quite a few trucks do very low mileage and nobody's over 25,000 a year. Whereas this one being skewed to the right shows that there's perhaps a slightly alarming number of days which are edging into that danger zone. So let's take a look at box plots for grown-ups. Here's the box plot we started off with. These 2 dots up here represent just 2 days out of the year. So these are our outliers. 363 of our readings are down there, just 2 of them are up here. Who decided to stop the main diagram at 120? The answer is a man called John Tukey. I'm just going to very quickly now run through how you draw a box plot to make sense of this. Here is some raw data, and just to explain, that's shorthand. 0 to 10 to just means 0 up to but not including 10, 10 up to but not including 20, and so on. Now, if I want to draw a box plot of that data, the first thing I have to do is draw a cumulative frequency graph, and in order to do that, I need to work out my cumulative frequencies. These are just my running totals of frequencies. When I present this information in the form of a cumulative frequency graph, what I do is I plot the upper end of these intervals, so 10 along the x-axis, at 35 up the y-axis, and so on. And that gives me this graph. I now find my median value by saying there are 365 days in the year. Half of 365 is 182.5. So up the y-axis to 182.5, look down, and we can see the median is about 37. I then find the lower quartile by halving that 182.5. That takes me to 20 on the x-axis. And then I go 3/4 of the way up to 365, which is about 275, giving me a value of 60 for the upper quartile. I then draw my box plot, first of all by drawing the box. Bottom end of the box lines up with the lower quartile, top end of the box with the upper quartile, and the line in the middle with my median. What Tukey said is I need to look at that distance there, the thing we call the interquartile range. We call this lower quartile Q1 and that upper quartile Q3. Q2, 2/4, is just the median. To get the interquartile range, I simply work out the sum Q3 minus Q1, and we can see Q3 is 60, Q1 is 20, so the interquartile range is 40. And what John Tukey said was that the whiskers should never be more than 1.5 interquartile ranges long. So, in this particular case, my whiskers must not be more than 60 units long, 60 parts per billion long on this scale. Well, down at the bottom there isn't a problem because I want to go down to 0, I've only got a gap of 20, so I'll just draw in that whisker in the usual way. But if I was doing this the GCSE way, I would now say, well, my biggest value is 167, so I'll go all the way up to 167 and draw my whisker up here. This is really scary because, as far as I recall from that data, the really dangerous level is up here at 150. Oh, goodness me, how many numbers are up there? Could be 10 days, could be 20 days, I don't know, but it looks like a lot. By drawing in what we call the Tukey hinges, or the whisker that just goes 1.5 interquartile ranges up, I draw it there, and I just put in separate dots for my top values. I get 1 dot at 139 and 1 at 167. Not as scary as it was. Histograms, much loathed by GCSE pupils, aren't that bad so long as you remember they're all about areas. I'm not going to go through how to draw one in detail here. You should be aware of how to turn the data in front of you now into a slightly reconfigured set of data like this, including completing the frequency density on the left-hand side, knowing what all that means, and calculating the heights of the missing bars. If you're not sure how to do it, there is a video alongside this one that goes through this specific example in a little more detail. So let's end by looking at a couple of charts and telling a couple of stories. And we'll start with a dual box plot, comparing the ages of male and female Oscar winners between 1975 and 2004. The obvious points are the ones you would have been expected to notice at GCSE. Female Oscar winners are generally younger than male ones, but on the other hand, the oldest performer to win between 75 and 04 was in fact a woman. The more important points that I want you to understand are, by comparing the median ages, we can say the median age of female winners is actually 7 years lower than the median age of male winners. By comparing the interquartile range, that magic window where half the winners are is quite a bit narrower for women than it is for men. You can also see that 3/4 of female Oscar winners have been under 42, compared to more than half of the men who are over that age. And finally, only 3 female winners have been over the age of 50, whereas over 25% of the men have been that age. Older women and older men are treated very differently by the Motion Picture Academy. Now let's look at another story, this time the story of annual salaries in the UK. Because incomes in the UK get so high, this histogram does not show the top 1% of earners. Well, the first thing that's quite striking is you don't need to understand frequency density to see what's going on. The numbers on the left don't really matter, but what you can tell is that very, very few people are on salaries of over 70,000 a year. In fact, the figures tell you that it's about 5%. You always sacrifice a bit of precision for the clarity that a diagram shows you. If we draw in a line here, that is where the higher rate of income tax comes in. 42,385 back in 2015, and you can see that it's actually not very many people who pay the top rates of tax in this country. So, with charts, it's hard to be precise, although you can state some figures, but you do get a very clear big picture if the chart's been drawn properly. But what happens when charts go bad? Here is a chart showing the triumphant progress that an airline has made in its punctuality this year. As you can see, in the financial year 2014, just 56% of their flights left on time, whereas by the financial year 2016, fully 63.6% were leaving on time. But hang on. Where's the y-axis? And how come 63.6% is double the size of 56%? It's because they haven't drawn the y-axis. If I drew this chart honestly, it would look like that. Things got a bit worse from 14 to 15, and a little bit better from 15 to 16. Not that spectacular. And some charts are just plain awful. What about this one here? Now, regardless of what the data's trying to show you, can you tell which line is which? That is a 3D comparative ribbon chart and is absolutely useless. Don't use 3D charts. They're far too easy to draw on a computer, but they generally don't make things clearer, and in this case, make it a lot harder to understand. Bad charts don't tell the story in an honest way, and sometimes just aren't clear. If you want to know more, you can look up bad charts on the internet. What about other charts? You'd have done a lot of these at GCSE. Pie charts are actually quite widely used in the media, but because they're not very good at showing actual numbers, beyond showing something like voting outcomes in an election, they're not really used much by statisticians. Stem and leaf charts are much beloved by GCSE examiners. Technically, they are in the core maths course, but they're not really used by anyone else out of the exam room. Make sure you can do them, but don't waste too much time on them. Now, scatter graphs are important, but they deal with a slightly different type of data. All the data we've been looking at so far has been what we call single variable data. We've been looking at salaries. We've been looking at the length of time people take to complete a task. We have one figure for each data point. In the case of a scatter graph, you actually have 2 figures for each data point, and they form the coordinates. We will look at those later in the course, but not right now. And then there are all the other ones that you can draw with your spreadsheet. Radar charts, pictograms, waterfall chart. We don't really bother with those. The ones you should be able to deal with are line graphs, great for time series. Bar charts, the simplest and often the best. Box plots and the associated cumulative frequency curves. And of course, histograms. You should be able to construct all of these charts, but most importantly, interpret. Tell the story of the data that lies behind them. Now, complete the tasks you have been set.